Hello everyone, I'm Fouad Bahrpeyma. I work as a postdoc in the Smart Production Systems group at HTW Dresden, Saxony, Germany. In this research, we propose the use of reinforcement learning to address the problem of optimizing the performance of a manufacturing system in the case of parallel operations in the presence of uncertainty in operation times. Today, I'm going to first explain to you about our IoT test bed at HTW Dresden, for which we try to propose an optimization mechanism. Then I'll talk about the challenges we face in this problem. Afterwards, I'll explain our methodology, followed by explanation of the results, and at the end, we see the conclusions from this research and the potential future works. Our IoT test bed has a variety of modules, each supporting a different set of operations such as milling, heating, manipulations, and pressing. We also have AGVs in order to facilitate transport inside the manufacturing environment. The assembly line operates in a loop architecture mainly, while has the ability to transform into a ladder architecture via the use of a set of switches on the conveyor belt. However, at the moment, we're not using the whole capacity of the system, and there are many ways by which we can improve the system. In the most basic form of this problem, we have 4 stations and 3 operations, and 2 stations support the same operation. Station number 1 supports operation A, station number 2 supports operation B, also station number 3 supports operation B, and station number 4 supports operation C. And at the same time, we have this problem of having uncertainty in the operation times, meaning that operations in machines can be performed in a margin of 1 to 3 seconds. And the overall objective of the scheduling algorithm is to minimize the mean waiting time. In a more complex form of this problem, we have 6 stations and 4 operations. The station number 2 and number 3 supports operation B, and the station number 4 and number 5 support operation C. Then we have an increased complexity, and the overall objective is also to minimize the mean waiting time. In total, for all these problems, we have to use as many parallel operations as possible in order to achieve the minimal mean waiting time. In order to explore the entire solution space, we need to consider all the contributing factors such as uncertainty, number of carriers, initial states, and decisions. As you can see in this table, increase in the possible values of the contributing factors will lead to an exponential increase in the solution space, which is significantly difficult and time-consuming for traditional optimization methods. These are the examples that I showed you before. In the first example, we have one parallel operation which is supported by station number 2 and station number 3. And in the second example, we have 2 parallel operations, operation B, which is supported by station number 2 and the station number 3, and operation C, which is supported by station number 4 and station number 5. In this research, we propose to use reinforcement learning to address this scheduling problem, while the objective is to minimize total waiting time or mean waiting time in the presence of uncertainty in operation times. Reinforcement learning is an algorithm that is specifically designed to deal with uncertainty. In a reinforcement learning problem, we have an agent which interacts with the environment of the problem space. Every time you want to do an action, it observes the environment state, and based on this observation performs an action, and for this action receives a reward. And the objective of the agent is to maximize this reward in an immediate or cumulative form in the future. So in the reinforcement learning problem, we have an agent, environment, action, state, and reward, and the objective is to train a model that gives us this policy. This policy returns an action based on the state. So these are the results. In this research, we use for popular reinforcement learning methods such as DeepQ network, reinforce, advantage, active critic, and proximal policy optimization. And these are the results for methods. As you can see in this paper, the best performing method was PPO in terms of the average score and the accuracy, and it competes with DQN for the speed of convergence. Just to let you know how we can interpret the results in the format of this box plot. On the left hand side we have accuracy, which is normalized between 0 and 1, and the average number of episodes on the right hand side that shows the required number of episodes until the convergence of the training process is achieved. One good thing that box plot figures provide us with is the variation of performance. As you can see, in terms of variations in the performance, A to C was the best performing method. However, the final result is important to us, and PPA outperformed the rest in terms of the accuracy and the total number of episodes required for convergence. And at the end, we could see PPO was the most effective approach in comparison with DQN, ATC, and Reinforce for the number of episodes required for convergence, the duration of training, and also the average score. The reason that PPO performed better than the rest of them was that actually PPO is a policy gradient method. However, it has a challenge of over-rewarded episodes. Future works contain increased the number of parallel operations, increased the dynamicity of the environment, and also exploring a more complex architecture. Thanks very much for listening to me. If there is any questions, I'm happy to be able to answer.